Bam. All right. So last time we learned implicit differentiation, where we took the derivative of y with respect to x, giving us dy over dx or y prime. Whatever, both notations are the same thing. Today's related rates, where we are now going to use the implicit differentiation with respect to time. So now we're going to take the derivative of x and the derivative of y with respect to time, as you see down here. So the notations, you have d over dt of x, which is going to be dx over dt, or I like to use the simple notation x prime. So now the derivative of x with respect to t is going to be x prime. And then the derivative of y with respect to t is dy over dt or y prime. And the same would go for any other variables being used. Okay, so some steps to solve a related rates problem. One, you're probably going to have to look up formulas for the actual problems, because it's going to say the area of a square, the area of a sphere. You're going to have to look up formulas to find those. And then, given the question, you're going to have to determine what quantities are changing with time and what are the other quantities and variables given. Find that equation, like I said, look up those equations. That's the power of Google's you can use. And after you figure out what equations to use, you're going to differentiate both sides with respect to time and solve for whatever the question's asking. We do not plug anything in until the very end. We try not to plug anything into the very end. If we plug in right from the beginning, the derivative is always going to be 0 most of the time. So we avoid plugging in any values until the very end. Okay. So let's go ahead and try it out. Number 1. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So for this one, we have to look up the formula for the volume of a sphere. I typed it there just for us, nice and neat. But when you are working these problems, you're most likely not going to be given the formula. So you have to go and search for these formulas. Okay, so here is the formula for the volume of a sphere. V equals 4/3 pi r cubed. And now we need to pick apart what this question is telling us. This says air is being pumped into a spherical balloon so that its volume increases at a rate. So remember, we are dealing with derivatives with respect to time. So the key word here you should look for is rate. So rate of change, slope, these all mean the derivative. And what this problem is telling us is that the volume is increasing at a certain rate. So is that going to be V or is that going to be V prime?
V prime.
V prime, yeah, woo. All right. So, because remember, V is volume. This means that V prime would be the rate that volume increases, right? So I guess I could write that down. V would just be plain old volume, and V prime would be the rate that your volume increases. I'm just going to say rate of volume. And this problem says, hey, our volume is increasing at a rate of 100 centimeters cubed per second. So they're giving us this value. Okay. And then it says, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So how fast is the radius of the balloon increasing? Are we looking for R or are we looking for the derivative of R?
Derivative of R.
The derivative of R. Good. So this means we're looking for R prime, the rate that the radius is increasing. I'll just keep it shorthand, the rate of the radius. Okay, so this is something that we're looking for, so we don't know. But if they're giving us that the diameter is 50 centimeters, then what is the length of the radius?
25 centimeters.
25 centimeters. Okay, so now we have labeled all our variables. We have picked apart the problem. And now we can go ahead and take the implicit derivative of this formula. Okay, so we're going to say d over dt of v equal to d over dt of 4/3 pi r cubed. Okay. Now the implicit derivative of volume is going to be dv over dt, or once again, I like to do the notation v prime. Just know they mean the same thing. dv over dt and v prime. All right. On the right side, well, I'm just going to take some terms and move them to the outside. And those terms are the constants or the coefficients 4/3 pi. The reason I'm taking this out is so you can see what we're actually taking the implicit derivative of. D over dt of r cubed. Okay. And now we take this implicit derivative and we get 4/3 pi times the implicit derivative of r cubed. This is going to be 3r squared r prime. And now, if we look above when we labeled everything, we are going to solve for r prime. So let's go ahead and rearrange this whole equation for r prime. So we get v prime equal to, and if I do the 4/3 pi times the 3r squared r prime, these threes will cancel. And I will be left with 4 pi r squared r prime. And now to solve for r prime, I just divide by 4 pi r squared. 4 pi r squared. And we get v prime over 4 pi r squared is equal to r prime. Which means now we can plug in the variables that we know. From the above, we know that v prime is 100, and we know that r is 25. So let's go ahead and plug them in. We're going to get 100 cubic centimeters per second over 4 pi times r, which is 25 centimeters squared. Okay. And now all we have to do is simplify. So this would become just 100 cubic meters per second over 4 pi times 625 squared centimeters. And now we'll just calculate. I think I have Desmos up. Let me see. Yep. All right, so this means I'll have 100 over 4 pi times 625. And yeah, that's good. So I'll get 0.012 0.127, I'll put that in there, centimeters per second. Okay. And there we go. So what we're saying is that as air is being pumped into this balloon, we know the volume is increasing, but we also can find out the rate that the radius is increasing. So as the balloon fills up, the radius of this balloon is increasing by 0.0127 centimeters per second. All right. Any questions on that? So pick apart the pieces of the problem, know what variables to assign, and then, find the formula that you need to work with, take the implicit derivative of it, and then you'll plug in all your values. So everybody good with this one? Hey, you got a thumbs up. One thumbs up. All right.
You did it.
We did it. Okay. Of course, we'll have more. So I know somebody who really loves related rates and would like to step in for a second.
Yeah, buddy. Yeah, buddy.
All right. Do you
All
need
about these related rates.
do you need my OneNote link?
Oh, no, I can do it on mine if that's all right. And then
Yeah,
later
that's
just
fine.
copy it over to yours.
Okay.
All right, let's see.
Oh yeah. Also, another form, in case you don't like using the prime notation, this could have been dv over dt over 4 pi r squared equal to dr dt, which is probably the notation Ryan's going to use.
I'll
Whichever.
try. I'll probably do my best to use prime.
But just know the reason I write this is just to show the comparisons that they mean the same thing. I just don't like these dv over dt's everywhere.
Yeah.
All right.
Boom. Look at that diagram already made.
Oh, wow.
Okay, so we're told that a 10-foot ladder rests against a vertical wall. So this purple is the ladder. And actually, my first question is going to be, does the length of this ladder ever change? No, the length of the ladder will never change, meaning I can plug in 10 feet for my ladder. The only times you cannot plug values into your diagram is if those values are changing. So in this case, the ladder does not change, so it is safe for me to plug in the number. Next is, if the bottom of the ladder slides away from the wall, meaning the base of the ladder is moving this way, it is moving at a rate of 1 feet per second. Well, this floor represents a horizontal axis. So I'm going to say that that is x. In this case, it's saying this is a rate. So this is going to be x prime. And that rate is 1 feet per second. Meaning the distance from the base of the ladder to the wall, I'm going to represent as a distance of x. And since this distance is changing, I'm not going to plug anything into my diagram for x. I'm just going to leave it as an unknown. It then asks, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so this is asking to find y prime. How fast is the top of the ladder moving down the wall? Well, since the top of the ladder is moving down the wall, y prime is going to be here, meaning the distance from the top of the ladder to the bottom of the floor will be represented by y. Okay. Now we need to find the relationship between y, x, and 10 feet. Well, let me emphasize the shape that this makes. Looking at the red dashed lines, what shape does the ladder make with the floor and the wall?
Triangle.
It's a triangle, right? So essentially, we have this, where we have 10 feet is the hypotenuse, x is the base, and y is the height of our triangle. Now, can any of you think of a relationship between the sides, the three sides of a triangle?
What is it called? A squared plus b squared equals c squared.
Exactly. Pythagorean theorem.
Yeah, Pythagorean theorem. Gosh, couldn't say
So
that.
x squared plus y squared is equal to, in this case, 10 squared. So now that we have the relationship between x and y, in order to find the relationship between the rates at which x and y are changing, all we have to do is take the derivative. So in this case, we'll take the derivative of both sides. You always take the derivative with respect to t. So now, the derivative of x squared with respect to t will be 2x x prime, right? Plus the derivative of y with respect, or y squared with respect to t will be 2y y prime. And the derivative of any constant will be 0, which makes sense, right? Because this 10 represents the length of this ladder. And since the length of the ladder is not changing, the rate at which it changes should be 0. So now we just need to solve for y prime, because y prime is what it's asking us to solve for. How fast is the top of the ladder sliding down when the wall reaches the bottom of the ladder? Or sorry, when the bottom of the ladder reaches 6 feet away from the wall. Okay, so now solving for y prime, I'll get, so subtracting 2x x prime to the other side, we'll have 2y y prime is equal to negative 2x x prime. Now dividing out 2y, we'll have y prime is equal to negative 2x x prime over 2y. Now that we have y prime solved for, this is when you start plugging everything in. So going back to what's given, we're told that x prime was 1 feet. And then we're told that we were 6 feet from the wall. So y prime is equal to negative 2 times 6 times 1 all over 2 times y. Because if we look back, it hadn't given us how far the wall, or where the top of the ladder was from the floor, right? That means we need to find what that value is. So what do you think we can do here? So we need to find how far the top of the ladder is from the floor when the ladder is 6 feet from the wall.
We could plug in the value of 6 into the I can't say it.
Good, right. So if we plug in 6 into our Pythagorean theorem, that should tell us how far the top of the ladder is from the base of the floor when it's 6 feet from the wall. So we'll have 6 squared plus y squared is equal to 10 squared. So this is going to be 36 plus y squared is equal to 100. Now we have y squared is equal to 100 minus 36. So now we'll have y squared is equal to 64. And then to solve for y, what am I going to have to do to both sides?
Square root.
Square root, right? But whenever we square root an equation, we get two solutions, right? We get a plus or minus. But remember what y is. Y represents the distance from the top of the ladder to the floor, right? So the question is can distance be negative?
No.
Distance cannot be negative. So all we'll have is the positive root of 64, which is 8. So that means when the base of the ladder is 6 feet from the wall, the top of the ladder is 8 feet from the ground. So now we'll plug in 8. And then solving everything, well, these 2's will reduce, right? So we'll have negative 6 over 8, which is negative 3/4. But this is the rate at which a distance is changing. So if we scroll back to our units are feet per second. So this is negative 3/4 feet per second.
You put feet over 3.
Oh, whoops. Can anyone tell me why it's negative?
It's
That's
going down.
Good, right?
Yay!
So are you a stickler like on exams on like notation, feet per second, cubic centimeter cube, centimeter cube?
You better have those units on there. If it's not a unit, if there's no unit, it's just a number. You need to have meaning behind your numbers, especially if you guys are going to be scientists, engineers, or whatnot. You're not going to want to leave units off on your work. So yes. All right. Cool.
Yeah.
Good job. All right. You can switch on and off unless you want the water tank one
Is that the,
where you make the geometric substitution.
let's see it. Inverted cylinder. Oh man. Yeah, I can do this one.
Yeah. All right. I quit. All right. See you guys tomorrow. Next week.
Okay. So we have a water tank that is in the shape of an inverted circular cone. So that means that our tank looks something like this, right? The base radius is 2 meters and the height is 4 meters. So the base radius, so remember this cone is inverted, so that means that this is referring to this radius. Oh no, it ruined everything. There we go. So this radius is 2 meters And this height is 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay. So we know that there's water that is being poured into this tank, right? And as water is being poured into this tank, the water level is increasing. So far, so good? Yeah, it's doing great. All right, perfect. Now let's refer to our rate. We're given the rate at which this water is increasing is 2 cubic meters per minute. Well, first keyword is that it's increasing, right? So we know that this rate needs to be positive. Next is we need to see what this rate is referring to. If it's referring to cubic units, that means it's referring to a volume. So this means V prime is equal to 2 cubic meters per minute. So far, so good? Okay. Then we're asked to find the rate at which the water level is increasing, or the water level is rising, when the water is 3 meters deep. So I need a variable to represent the height of this cone, or represent the height of the water. So I'm just going to say h. In this case, we're asked to find what h prime is. Now, to find the relationship between the volume and the height, it's actually given right here, isn't it? The volume of this cone is 1/3 pi r squared h. So if I take this relationship and differentiate it, that will give me the relationship between v prime and h prime. So v is equal to 1/3 pi r squared h. Now we have an issue here, right? Going back to our question, is there ever a time where this thing gives us a rate at which the radius is changing? Because that's what r is, right? It's the radius of this cone. No, right? It just tells us the rate at which the volume is changing, and we need to find the rate at which the height is changing. In other words, we need to somehow get rid of this r and get this relationship in terms of just volume and height. So this is when these get a little tricky. I'm going to draw a triangle within this cone that will represent the radius and height of this water. Since the height and the radius of this water is changing, I'm going to represent them as unknowns, r and h. Now, do you guys remember setting up proportional triangles? The radius of this cone and the height of this cone share the same angle as the radius of this water and the height of this water, meaning that they should be proportional. So I can set up an equation that equates these two things. R over h is equal to 2/4. Oh, is my mic broken?
Not yours, hers.
Oh,
I can hear you.
Yeah, yeah, you're
Okay, cool.
good. You're good.
Cool. So now I just need to solve this equation for r. So to solve for r, I just multiply both sides by h. So 2 force h. And some of you might have the question, well, does h have to be in the denominator? It doesn't matter. All that matters is that the ratios between these two things, the numerator is either the height and the denominator is the radius, or the numerator is the radius and the denominator is the height, meaning that horizontally, those two things are both representing my height. These two things represent my radius. Those are the only things that matter. So now we have r in terms of h. That means I can go back to my volume equation and substitute in. So instead of r, I now have 2 force h squared. Oh, I can just write that as 1/2 h squared times h. Now I know I plan on taking the derivative of this, so let's go ahead and simplify this a little more. So 1/3 pi times, and then this power is going to distribute to both of these values. So 1/2 squared is 1/4 h squared h. Now I'm going to simplify by multiplying my like terms together. So we'll have 1/12 pi h cubed. So with all that being said, volume is equal to 1/12 pi h cubed. So far, so good.
Going great. I'm just crying. This is,
You-
oh man.
You get a
Okay.
thumbs up.
So remember, the steps for related rates is really just draw the diagram, identify the relationship between your unknowns, and then just take the derivative. And then from there, you just plug everything in. So right now, we've identified the relationship between our unknowns. Next step is to take the derivative. So if I take the derivative of both sides, we'll have v prime is equal to, and remember 1/2 pi, those are just coefficients. So I'm leaving those alone for now. And the derivative of h cubed will be 3h squared h prime. Now all of these terms are multiplying together. That means I can reduce this 12 and this 3. So we'll be left with 1/4 pi h squared h prime. And that is equal to v prime. So remember, the question was asking us, find the rate at which the water level is rising. So h prime represents the rate at which the water level is rising, meaning I need to solve this equation for h prime. So if I divide everything out by the coefficients of h prime, we'll have 4v prime over pi h squared is equal to h prime. So there's the relationship between the rate at which the volume is changing and the rate at which the height is changing. Now we get to plug in. So going back to what was given, V prime is 2. And the height at which we're evaluating is 3 meters. So V prime, again, is 2. H is equal to 3. So now we have 4 times 2 over pi times 3 squared equal to H prime. So we'll have 8 over 9 pi. And then going back to our units, we were meters per minute. And since this is just a one-dimensional unit, right, it's just height, the meters is just meters to the first power. That's it.
Ooh.
So I just got one quick question.
What's
When you divided the 1/4 pi, how did that 4 go on top?
Oh, so if I divide by 1/4, that's the same as multiplying by 4. So I multiplied both sides by 4.
Gotcha, gotcha.
All right. Good stuff. Keep going if you want. You got this. So,
Jeez. What's this next one?
it's another triangle
Can I-
one.
See the oh
What was
can I
that?
see the
Someone's
bottom?
asking. Someone talking?
He's breaking up, yeah.
Oh.
Maybe he wanted to see the last part. I don't know.
Is that good? Yeah. Thumbs up. Thumbs down.
Halfway thumb. Halfway thumb. Hmm? Yeah, this one's another easy one.
Ew. Cars.
Pythagorean theorem.
Okay. So car A is traveling west at 50 miles per hour. All right. So here's my little car A. It's going this way at a rate of 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for the intersection of 2 roads. Okay. So we'll say that car B is somewhere down here, right? So here's car B.
Intersection, yes.
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 Car B is traveling at 60 miles per hour. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so let's write what's given to us in terms of unknowns, right? So car A is traveling west, meaning it's traveling in a horizontal direction. So I'm going to say X prime will be 50 miles per hour. Car B is traveling north, meaning it's traveling vertically. So I'm going to say that's Y prime is 60 miles per hour. I should say miles. There we go. It's not meters. Dumb imperial units. And it's asking us the rate at which the cars are approaching each other at these given distances. So we'll say at x equals 0.3 and y equals 0.4. So as these cars approach this intersection, this distance between them is getting smaller and smaller and smaller. So if I draw this relationship as a diagram, there will be a triangle. So this is the path at which car B drives, this is the path at which car A drives, and this is the distance between those two cars. Car A's path is represented by X, car B by Y, and the distance between them we'll just say is Z. Meaning this question is asking, what is Z prime? So now I need to find the relationship between X, Y, and Z. What do you think that relationship is going to be? Sean Connery's theorem.
Pythagorean theorem.
Yeah, Pythagorean theorem.
Pythagorean theorem.
Right. So again, x squared. Whenever you're dealing with the sides of a triangle, with these problems in particular, you're pretty much always going to assume they're going to be right triangles. So if you're ever given sides and asked to find a third side, it's always going to be Pythagorean's theorem. All right, so now that we have the relationship between our triangles, or sorry, our sides, let's try taking the derivative. So d over dt of x squared plus y squared is equal to, and d over dt of z squared. All right, say taking the derivatives of these with respect to time, we'll have 2x x prime plus 2y y prime is equal to 2z z prime. Now scrolling back to what's given, we were told what x and y were, but we don't know the distance z is at these given x and y values. So like what we did to the first Pythagorean theorem problem, we're going to take these x and y values and plug them into our Pythagorean's theorem. So we'll have 0.3 squared plus 0.4 squared is equal to z squared. And then plugging those in, 0.3 squared plus 0.4 squared. So this is 0.25 is equal to z squared. And then the square root of 0.25 be just 1/2. And again, since we're dealing with a distance, we won't take the negative solution, we'll only take the positive solution. So z will be equal to 0.5. So now that we have z, we plug everything in. So we'll have 2 times, and then it was 0.3, and then x prime was the rate at which x was changing. So x prime was 50. Plus 2 times 0.4 times 60. Is that right? Yeah. is equal to, and then z was 1/2. So we have 2 times 1/2, which is just 1. So we have z prime. I guess I should write that out. So we again 2 times 0.5 times z prime. So then we have on this side just z prime, and then plugging everything into our calculator, we have 2 times 0.3 times 50 plus 2 times 0.4, 60. And we'll get 78 miles per hour.
But shouldn't this answer be negative?
Oh, right.
Technically?
Good. So the distance between them is, if we go back to our solution, or sorry, if we go back to the problem, this distance here is getting smaller and smaller and smaller, meaning the rate needs to be decreasing. So this is going to be a negative 78 miles per hour. Because again, the distance between those two cars is decreasing.
Only because we assume they're normal human beings who are slowing down towards an intersection.
Right.
Yeah. But yes. Cool, man. Hey, you got it. One more.
Oh,
Your money's
no.
worth today.
Not this goon street lamp thing. Okay.
At least it's not the one with the shadow. Cool.
Oh, yeah. Okay. So a man walks along a straight path at the speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so here's our dude. He's walking in this direction, and he's walking at a rate of 4 feet per second. Since he isn't Spider-Man, right? We're going to assume that he's working on a horizontal distance. So we'll say that x equals 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. So I guess is the searchlight ahead of him?
Well, it could be however you set it up. But if it's following him, I'd assume it could be, you could either have it on the bottom right or you can put it on the bottom left.
Yeah, so we'll do it like this. So here's our searchlight. And our searchlight is keeping an eye on him, right? And as he walks on this path closest to them would be represented by here, right? So this is where the man will end up. And it's saying at what rate is the searchlight rotating when the man is 15 feet from the point on path closest to the searchlight. Okay, so that means we're having to find the angle at which it is rotating, meaning we need to find theta prime. Look it into the ground. And this distance, so this distance here, I'll do a different color. I'll do red. Is the distance from the searchlight to the path at which the man is walking. And since this searchlight is not moving away or towards that path, his path is a constant 20 feet. So if you imagine he's walking on like a street. So what color? Purple. So here's our street. The man is walking along the street and the searchlight is monitoring him walking. And when he's on the path closest to the spotlight, that essentially means that it's the distance from the spotlight to the street that he is walking on. Does that make sense? Where's that thumbs up? I don't see any.
Sure.
Okay.
Sure. I'll take a sure.
Okay. So we need to find the relationship between, in this case, the distance that the man had walked will be represented by x, and the angle, which is theta. So let's redraw this triangle a little bit more clearly without all the diagrams of people in spotlights. Guess I'll do it a little. So here is the path. Here's the distance from the spotlight to the path. And then here's the distance between the spotlight and the man. So here's the distance x. Here's the angle theta. And again, the distance between the spotlight and the path do not change. So that distance we can plug into our diagram. So you guys see that this is, we can assume a right triangle. So what is a relationship we can create between theta and x?
What do you mean relationship?
What trig function?
There you go. There you go. Well, I mean, we kind of know the value of x though, don't we?
Let's see, what were we told?
So he's walking at a rate, but then on that path, he's traveled 15 feet so far.
Oh, so is it like x minus 15 or something?
No, it's just 15. That's why this diagram's a little hard to think of. Like, I think if you drew that from this diagram that we're looking at, if you had the arrow going the other way, and where the blue guy is, that would be the 15-foot mark from the closest point on the path.
I think, wouldn't that be if this spotlight was over on this side? Because it's asking from when he's closest to the spotlight.
Yeah, because normally, here I can annotate. Let me see. Because normally I draw it, I just do this, and I have my spotlight there. And then the man is walking that way.
I don't see anything that you were doing.
Oh,
Yeah.
I'm drawing. I'm drawing, but it's disappearing. That's weird. Anything? You get that? Oh, maybe it's all going to show up. Hang on. Maybe if I draw on my laptop. Let me see.
So could we say like Green Man is where he started?
Yeah,
and
because
he's walked 15 feet.
But so if green is where he started and then light is here, where he ends up would not be the path closest to the light. Because that's
Well,
what it's saying.
it's
It's
like
15 feet from the
15
point.
from the point
Oh, I
on the
get you.
path.
Gotcha.
Yeah. So it's
Okay.
like it's
Gotcha.
away from
There
that.
you go.
Yeah. See, this
Stupid
is why
man.
we're math majors and
There
not
we go.
English majors.
So that
This
means
is-
this is rotating this way.
Yeah, this is why related rates is so hard because I
There
can't
we
read.
go. Well, we still can't plug in x yet, right? Because
Yeah,
this
Well, you want
is
to
just
define.
this diagram.
I think we'll need it to find the distance from the hypotenuse.
Right, but
But
I'm
you
just
don't
trying to
wanna-
find the relationship between x and theta as of right now.
Yeah,
But then later, we will have to plug in that 15 to find out
exactly.
what theta is. Right. Listen. Okay, So we're good, right? So he
Yeah, we're
started
good now.
he started parallel with the lamp because that is the path closest to the lamp. Then he started walking away and the lamp was rotating, following him as he was walking. So this is saying how much has theta changed? So when x is equal to 15 feet, given that x prime is 4 feet per second. Okay. So now we have a series of unknowns, but we do have a relationship. We have this triangle which shows the relationship between theta and x. So which trig functions would you guys use to show the relationship between theta and x? Tangent.
Wouldn't we do tangent theta equaling x over 20 or something
Good.
like that? All right.
Exactly. Tangent of theta would be the opposite. In this case, the opposite of the angle would be x over 20. So far, so good? Yeah, super easy. Sweet. So now that we have this relationship, we can take the derivative of both sides with respect to t to find the relationship between the rates at which they are changing. Okay, what is the derivative of tangent of theta? Let's scroll up just a bit. Yeah.
Secant squared?
Secant squared theta. But remember, we're taking an implicit differentiation. So you take the derivative of tangent theta like you would normally, and then just multiply it by theta prime. And then the derivative of this would just be 1 over 20 x prime. So far, so good?
Yes.
Now, like we were saying earlier, we don't know what theta is. So now we need to find out what theta is when x is 15. So if I plug 15 for x, we can actually use our original relationship. So tangent of theta is equal to 15 over 20. So tangent of theta is equal to 3 over 4. And then from here, if we're solving for theta, we would have to apply the inverse to both sides, right?
No. Remember, we don't need to know what theta is exactly because we're solving for theta prime. So you can use trigonometry.
Oh, sorry, I'm being a
Yeah,
goon. Okay,
Yeah.
so we just need to solve for secant theta, right? Knowing that x is 15. So remember, secant is the reciprocal of cosine. And cosine is adjacent over hypotenuse. So I need to find out what this third side is. So what do you guys think we're going to use to find that third side? Say that third side is z.
Pythagorean theorem.
You know it. 15 squared plus 20 squared is equal to z squared. So this means we have 625 is equal to z squared. And then if I square root both sides, remember z is a distance. So we're only taking the positive solution. So that means z is 25. So when x is 15, z is 25. Now we can use this triangle to find out what secant theta is. So secant theta would be the hypotenuse over the adjacent. So 25 over 20, which is 5/4. So going back to our related rate, we have 5/4 squared times theta prime is equal to 1 over 20 times, and then x prime was 4. So this is going to be 25 over 16 theta prime is equal to 1 over 5. Now to get rid of this 25 over 16, I'm going to multiply both sides by 16 over 25. So just multiplying by the reciprocal. We have theta prime is equal to 1 over 5 times 16 over 25. And that's going to be 16 over 125. And this is the rate at which an angle is changing. So this is radians per, and then we were given seconds. Yay!
Yeah, you did it.
I have a question. So rather than solving for data itself, you basically just got the whole secant data value and plugged that in instead.
You know it.
So
It would
I
have given you the
couldn't-
same answer.
Okay, so even if we wanted to solve for data itself, we would have gotten the same answer?
Yeah, but
Okay,
if you solve, you would have to use, because solving for theta using this triangle, it wouldn't have been on the unit circle. So you would have to apply inverse trig functions. And then you would have to think of the restrictions of those inverse functions. So it ends up just being a lot more complicated,
okay.
right? So instead, we just did a direct substitution. We found out what secant theta was, and then just plugged that number into our equation.
Yeah.
Well, all I can say is that you're gonna see me a lot in office hours. That's great.
Sweet.